have already seen that two events that are synchronized in one reference frame are not synchronized in another reference frame. We have also seen that the measurements of time depend on the observers, depend on the reference frame. The time of a moving clock is slowed down with respect to a clock that is at rest. These are the first two effects on measurements on time. So we have that time itself is not rigid anymore, as Newton thought. Time is something flexible. But what about space? What is the relationship between the measurements of space, of distance, in two reference frames? We're going to perform another Gedanken experiment. We're going to build another light clock on a train and observe its behavior. First from the train and then from the station. Let's grab our source of light. This could be a pulsed laser, a laser that sends pulses of light. We placed this source of light on the back wall of our train wagon. On the other wall, we place a mirror. Light will be reflected off of the mirror. The train moves to the right at speed v. Light goes back and forth at speed c. The doctor is on a train and measures a speed of light to be c. When the pulse of light turns to the doctor, she detects the pulse and determines the time of flight of the pulse to be t naught. From this time measurement, she calculates the distance traveled as L naught. She can write the length of the train wagon as 1/2 of ct naught. Then we have Missy on the station. She is observing the experiment of the doctor. She sees the pulse of light go from the rear wagon to the front wagon, and the reflection from the front going back to the rear of the wagon. But while the pulse is traveling, the train is also traveling, as seen from the station. The first trajectory of the pulse of light needs more time to reach the mirror because the mirror is moving away. When the pulse of light has been reflected, it will need less time to reach the rear mirror as this latter is going towards the light pulse. Let me split this process in two parts. The distance traveled by light going forward, L1, will be the length of the wagon L plus what the train has moved. The train has moved a distance Vt1, so the distance traveled by light is L plus Vt1. When light goes backwards, light travels the length of the wagon minus what the wagon has moved. Now we can write the distance traveled by light as c times the time that Missy measures from the station. So we can write L1 as ct1 and L2 as ct2. Let's calculate the time the light needs to go back and forth as seen from the station. This is t1 plus t2. Let's do some wibbly wobbly timey-wimey math stuff. Here we have the time of flight of the pulse of light from the station reference frame. As this result here, where we introduced again the beta factor. Now we have a relationship between the length of the wagon and the time of flight, both from the station and from the train. We found in the previous lesson the relationship between the time measurements between both reference frames. Now we want to find the relationship between the measurements of length. Any ideas? Any intuition? If the speed of light is the same for all observers, and the speed is distance over time, if the measurements of time are not the same for both observers, let's grab the previous results, and I will divide L0 over L. At this point, I will recover the result we found for time. Time measured on the station is equal to time measured on the train over this square root. Wibbly wobbly timey mathy stuff, and so the length measured from the station is not the same as the length measured from the train. Here too, measurements of distance depend on the observer. Because this square root is smaller than 1, this means that the length measured from the station is smaller than the length measured from the train. Lengths of moving objects contract in the direction of motion. Time dilates and space contracts. While the speed of light is absolute, the same for everyone, space and time are not rigid. They are plastic. They do depend on the speed of the observer. To recap, we have found that synchronization depends on the observer. Measurements of time depend on the observer, and measurements of space depend on the observer. Take home message: if you want to stay young and slim, run fast, and may the science be with you.